Welcome. I'm Liz, and if you've ever struggled with tough questions about the excretory system before, you're in luck because this lesson is all about kidney function. We'll get started by taking a look at the different major roles of the nephron, and then we're going to move into talking about the different factors that can change urine production. Let's get started. Take a few moments to read through the given scenario. Personally, I'm a sucker for diet soda, so this student's predicament is very near and dear to my heart. If any of you also love diet beverages, this is a good lesson to consider taking to heart for test day as well. You don't want to have to get up from that computer unless it's a scheduled break, so it may seem a little bit obsessive, but you want to pay attention to things like this. Anyways, our student in this scenario has noticed that his or her current urination issues coincide directly with intake of those diet sodas, and he or she wants to get to the bottom of this. We don't have a ton of other info on the student, but we'll arbitrarily make a male for the ease of my pronoun use. We also know this sweetener isn't processed in the way that glucose is. With that information, let's start thinking about what's happening in this guy's kidneys. Our first question to consider is really how the functions of the nephron itself relate to one another, the basic biology that underlies this kind of complex problem. If you're thinking about the kidney and how exactly the nephron works, you'd want to start with what the nephron is actually acting on, blood. What's the first major function of the nephron, and where does it occur? As the blood enters the glomerulus, some components are able to filter through the capillary bed into the Bowman's capsule. This first act, filtration, ensures that large blood components, such as the red blood cells themselves, never enter into the Bowman's capsule of the nephron. After all, we really don't want blood getting into our urine. Those components of the blood that are able to enter the nephron are called the filtrate, as they now must be either reabsorbed or excreted. If a substance is reabsorbed from the nephron, it passes back out into the blood again. What about the substances that are being moved in the other direction, from the blood into the nephron after the glomerulus interaction? What's that type of movement called? If something is being moved from the blood into the nephron at some point other than at the intersection of glomerulus and Bowman's capsule, it's being secreted. This means it's being selected, as a way of putting it, to ultimately be excreted. So secretion tends to lead to excretion. That very specific selection of only certain wastes to secrete to be excreted as urine is one of the major functions of the kidney. Now let's get to our first prompting question. Given what we now know about how these processes are related, what would happen in the nephron if reabsorption decreased or if secretion increased? If reabsorption decreased, then there would be less material being returned from the nephron to the bloodstream. So we'd wind up with less materials moving out of the nephron into the blood, more materials making it all the way through the collecting duct, and more urine overall. Likewise, if secretion were to increase, more material would be moved from the blood to the nephron to be ultimately excreted via the collecting duct as urine. Let's figure out how this relates to our specific scenario situation. We were told our dude drank caffeine, which inhibits ADH. What's the normal function of ADH? Let's start with where ADH acts. ADH typically acts on the collecting duct, that last portion of the nephron where the urine becomes concentrated. Without any hormones present, the collecting duct is impermeable to water. There's no way for water to exit, and that means no way for the urine to get more concentrated via the exit of water. This is one of those big take-home facts about the kidney. It is not all permeable to water, meaning that not all cells in the body are always permeable to water. One of those big facts you should just know. If ADH, or antidiuretic hormone, is introduced by production of the hypothalamus, water channels become available within the collecting duct due to the action of ADH, and water in the collecting duct can be reabsorbed back into the blood. This means the content of the collecting duct can actually become more concentrated as fluids flow through it, and that the more concentrated filtrate can be excreted as urine. This is usually desirable when the body needs to adjust its osmolarity to a lower value and hang on to a bit more water relative to salts, which can occur due to mild dehydration, the need to clear toxins, or a myriad of other reasons. So let's think about what caffeine is going to do to the whole situation. With caffeine present, ADH is inhibited. What won't be happening as a result? Following our logic from before, no ADH means no water channels, water won't be reabsorbed at the collecting duct, and the urine will remain relatively dilute, kind of matching with that distal convoluted tubule concentration. Not a great situation if the body needed to change its osmolarity. And remember, with more dilute urine, you should be thinking more urine in general. Now let's consider just how much soda our person was consuming. They apparently drink a ton. Maybe they sprung for that 128 ounce at a gas station. Let's start with thinking about our person prior to the soda. What hormone would usually be active in maintaining overall blood volume in the human body? In a normal human system, there's always some basal amount of salt being pumped into and out of the nephron by the sodium-potassium pump. This is especially true of the distal convoluted tubule, one of the major sites of hormone action in the kidney. If there's a change to the system, the renin-angiotensin system is responsible for leading to the production of the hormone aldosterone. Aldosterone primarily acts at the distal convoluted tubule to increase the number of sodium-potassium pumps present. This increase in sodium-potassium pumps means more sodium is being reabsorbed and more potassium is being excreted, with a net effect, just like every time a sodium-potassium pump is used, of increased ion reabsorption on the sodium side due to the imbalance of ion movement by sodium-potassium pumps. That reabsorption leads to increased osmotic movement of water following the salt back into the blood, meaning that blood volume goes up without changing the osmolarity of the blood itself, as both salt and water are being reabsorbed. What would the consumption of soda do to this system? Lots of soda means lots of extra fluid in the system. Your body's thinking, wow, we've got a lot of water to work with, and it's being absorbed into the blood. So the body doesn't want renin to be present. Blood pressure and blood sodium due to the soda's contents are already pretty darn high. Decreasing renin release leads to a decrease in all subsequent steps in the pathway. And no aldosterone means there won't be any increase in reabsorption of sodium, that following osmotic movement of water from the distal convoluted tubule. Now let's address that final piece of this puzzle, the artificial sweetener. Most artificial sweeteners are undigested by design. No digestion means no use of those molecules to generate energy or fat, which is, after all, kind of the goal of a diet food. These substances often look and act like sugar in some ways, such as the way they taste and sometimes how they're absorbed from the digestive tract. But they're unable to use most typical sugar channels due to the specificity of cellular machinery made for glucose or other digestible sugars. So, what happens to a substance that can't be digested and isn't intended for energetic use by the human body if it makes it into the nephron through filtration? Normal sugar would definitely make it into the nephron, so we would expect an artificial sweetener to make it in as well. They're both small enough to pass right through that glomerulus into the Bowman's capsule. Normal sugar would then be reabsorbed right away in the proximal convoluted tubule, and water would follow it out via osmosis to maintain isotonicity. Asulfame potassium, though, can't be reabsorbed, meaning it would stay in the nephron, and water would stay in with it. Again, kind of maintaining isotonicity, those osmosis rules. Eventually, the asulfame K will make it all the way through to the bladder, and water is going to follow right along with it. So, more water is going to be excreted than usual, thanks to the presence of asulfame K in the blood and then in the nephron, holding water in the nephron with it. The net effect of all the forces acting on our guy, with increased incoming liquid driving blood volume up, caffeine preventing water reabsorption, and asulfame K driving water excretion, we're looking at a very fast increase in the quantity of urine produced and probably how often he has to pee. Each effect on its own could potentially be problematic, so this is something to keep in mind for yourself whenever you're drinking non-water beverages. In this kidney lesson, we took a look at the different basic functions of the nephron and how they would change in response to a specific situation, how those changes due to diet soda would ultimately affect urine production. This kind of tough application question is going to be kind of common on the MCAT, so you do want to be able to logic through it. Plus, there's the added benefit with problems like this one that you can actually apply this logic to your daily life as well. Remember as well that this content is going to be incredibly high yield, so you will want to take the time to make sure you know your regions and functions of the nephron and the endocrine hormones that interact with it for testing.